So we're going to take our increasing and decreasing functions one step further today, and today we're going to talk about the first derivative test. Okay, so basically, we're back to our critical numbers again. So if C is a critical number of f and it's continuous, now continuous is a really important thing, so I'm going to underline it here, on an open interval I containing C, that's our critical number, and f is differentiable on the interval except possibly at the value C, then f of C can be classified as the following. So 1, if f prime of x changes signs from negative to positive at C, then f has a relative minimum at the point C f of C. So that means, right, let's connect it to the last lecture, is if my derivative is negative, that means it goes from decreasing, and then I'm at the point C, and then to positive means it goes to increasing. So my graph is going from decreasing to increasing, and that looks like this. So decreasing is falling, right? And increasing looks like this. So of course, this is what we call a relative minimum point, right? It gives me a low point on my graph here. So that's the first thing. So if it's continuous there at that point, at our critical number, and my derivative changes from negative to positive on each side of C, then I have a picture that looks like this, meaning I have a relative minimum. Then I take my C value and I put it back into original f to find the other y coordinate. All right, so the second one is that if f prime of x changes sign from positive to negative at C, then f has a relative maximum at the point C f of C. So this means I'm changing in the opposite direction. So this time I have a positive slope, meaning I have increasing on the left of C, and then I'm decreasing on the right. So that means increasing looks like this, right? Decreasing looks like this in terms of slope. So that means I'm going to have a relative maximum point up here, right? That's my at C, right? And then the last thing just says that if f prime does not change sign at C, then it's neither a min or a max, okay? So let's put this all together and do a couple of examples. All right, so we are going to find the relative extrema of f of x equals 2x cubed minus 3x squared plus 36x plus 14. Right, so first of all, we need to find our intervals of increasing and decreasing before we can apply our first derivative test. So that means I need to find f prime. Intervals of increasing and decreasing and relative extrema mean I need to find my derivative. So I'm just going to apply my power rule here and get 6x squared minus 6x plus 36. So my critical numbers come where my derivative is equal to 0. I'm not going to have any place where my derivative is undefined this time, because that would come where the denominator of my derivative would be 0, and since I don't have a denominator, I'm not going to have any undefined places. So I want to know where this is equal to 0. I'm going to just divide everything by 6 because now it's equal to 0. So that would give me x squared minus x plus 6. So I just divided each one of these things by 6. And I also really technically divided the 0 by 6 as well, but then I still get 0. All right, so my zeros are at, I can factor this. So, right, these techniques, they never go out of style. I get x equals 3 and x equals negative 2. So these are the critical numbers of my first derivative. So now I want to find my intervals of increasing and decreasing. So I'm going to put my values on my number line. I get negative 2 here and positive 3 up here. So this f is a polynomial function that doesn't have any domain restrictions on it. So I know that if it changed signs at negative 2 and 3, it will be a min or a max, because there are times when my critical numbers result in a place where my original function is undefined, and in that case, my function isn't continuous there. So even if it would change signs there, it wouldn't be a min or a max. We'll come across one of those later. But for right now, we just know that it'll be continuous everywhere. So now I want to know whether my function is increasing or decreasing in each one of these intervals. So I'm just going to label these. This one would be negative infinity up until negative 2. That's that interval. Negative 2 to 3, that's that interval, and 3 to positive infinity. So I'm just using interval notation right now. So I want to test a point in each one of these intervals. So these critical numbers right here, they break my number line into this, this, and this. So now I'm going to pick a point and I'm going to test it back in my derivative because I want to know if it's increasing or decreasing, and it's my derivative that tells me increasing or decreasing. So I'm going to use f prime of -3 just to start. So I'm going to plug it into my nice factored version because I really only care about the sign of my derivative. So if I plug in -3, -3 minus 3 is negative, and -3 plus 2 is also negative, and so I get a positive result there. That means my graph of f is increasing there. All right, so now I'm going to pick a number between -2 and 3. I like 0, and if that's the case, right, I'm going to get basically -3 times +2, which is negative. So I get a negative value in here. And then I'm going to choose f prime of, I'll just use 5. Anything larger than 3 is good. If I plug 5 in here, I get positive. 5 in here, I get a positive. Positive times positive gives me positive overall. So my function, if I wanted to write them out, is increasing in these two intervals, the ends, right? From -infinity to -2, and from 3 to +infinity. And it's decreasing. Now, this is really kind of extra, but because all I was asked for is to find the relative extrema, but it's a good practice. It's decreasing between -2 and 3. So now I need to apply my first derivative test. My first derivative test basically says that if I am continuous at my critical numbers, then if my derivative changes sign, that it's something, okay? It's just a matter of the order that it changes sign. So I always like to think in terms of, okay, well, what does positive slope looks like? Well, positive slope means I'm increasing, right? My graph is rising. Negative slope means my graph is falling. And so based upon that picture, I have a relative max at -2 and f of -2, which we'll find out here in a minute. All right? So let's see. Now what else? I also have a sign change here, but this time I was falling, right? I'm decreasing, and then I'm increasing. So that gives me a relative min at 3, f of 3. So my last part is just to take my numbers and pop them back in here. Okay? So I would plug in my -2 into f to find this value, and I believe I'm going to get, you can do this on your own. So I think that this is -2 and +58. That's my max. This is the value that it happens at, and then this is actually the max value. And I get then I get also 3 -67 as my minimum. And I find these values here. Oops, sorry about that. I find this value, right? I plug this into my original f up here. This is f. And I find out that this is what I get out when I put them in. So this is my max and my min, my relative. So it means not necessarily overall, but just in that vicinity. And that's because I went from positive to negative at -2. So I found out, okay, that's a maximum. So then I take that -2, put it back into my original f. That's my maximum in that area. Okay? Same thing with the min. All right, so let's move on to a little bit more algebraically challenging derivative. So this one I'm going to do the same thing. I want to find the relative extrema. I'm not sure that I've said it or not, but every graph does not necessarily have relative extrema. I might have a min with no max. I might have a max with no min. I could have neither. Okay, so just because we don't actually have to have a min and a max. Now, if we were in a closed interval, then that's a different story. But if we're on the open number line, then my graph does not have to have extreme values. All right, so if I find my f prime of x, I have a chain rule, so that means I'm going to multiply my power in front, 2/3 x squared minus 4 to the negative 1/3. So that's the derivative of the outside. Then I multiply by the derivative of the inside, which is 2x. And so I'm going to move some things around here. Okay, so I have 2/3, this is my f prime of x, is equal to times 2x, because this is on top, and then this negative exponent means that I'm really in the bottom. So I have x squared minus 4 to the positive 1/3. So this is going to have a place where my derivative is undefined. So my critical numbers of my first derivative are either where the numerator is equal to 0, that's where f prime of x is equal to 0. So I get 0 is equal to 4x when I multiply those together. So I get x equals 0 is one critical number. Also set the denominator equal to 0. I get 3 times x squared minus 4 to the 1/3 power is equal to 0. I can divide by 3 and I'm going to get just this factor. I can raise each power to the third, and I'm going to get just in the end I get x squared minus 4 is equal to 0, which gives me x squared equals 4, which gives me both x equals plus and minus 2. Now x equals plus and minus 2 were places where my derivative did not exist. However, they do exist up here because this is a 2/3 power, so there's no domain restriction on f. So f is completely continuous, but the derivative fails to exist at positive and negative 2. So again, I don't have to worry about a place where my function isn't continuous. All right, so these are my critical numbers again, and so this breaks me into a few more intervals. So I have negative infinity to negative 2. This one's between negative 2 and 0. This one's between 0 and 2, and this one goes from 2 to infinity. Okay, I'm going to test a point in each one in the derivative again. Okay, so let's see. Let me choose, I'll do f prime of 3, negative 3, because I'm choosing a 1 in here. If I plug in negative 3 up here, right, then I'm going to get a negative value on top, because 4 times negative 3 is negative. And then if I plug in negative 3 down here, and this is going to be 9 minus 4, which is 5. 5 to the 1/3 power, hold its sign, it's still positive, times positive 3, so I'm going to get a negative divided by positive, which makes it negative in this interval. Alright, so now I need to choose, the only integer between negative 2 and 0 is 1, so let me try f prime of 1, of negative 1. So again, I'm going to get a negative value on top, because 4 times negative 1 is negative, and then I plug in negative 1 down here. I get 1 minus 4, which is negative 3. The third power will hold its sign, so this will be negative times a positive, which gives me negative overall, which means it's going to be positive right there. Okay? All right, so if I choose a positive 1 then, this time to put in my derivative, I have f prime of 1. This will be positive on top this time, because now I'll have 4 times 1, and I'll still have a negative value here, because when I plugged in negative 1, it would be the same in the bottom as when I plug in 1, because the negative 1 was squared. So this will still be negative on the bottom. So I'm going to get a negative value in this interval. All right. And let's see. Now I need one more. So let me choose f of positive 3. I will get a positive value in the top, positive 12 in fact, and a positive value in the bottom, so I get a positive value here. Okay, and so I'm changing signs at all of these places, right? So here I go from negative to positive, meaning I have a picture that looks like this. Here I'm going from positive to negative, and here I'm going from negative to positive again. So I have 3 different relative extrema. That is certainly possible, right? So I find that negative 2, f of negative 2, is a minimum. I find that 0, f of 0, is a max. And I find that also 2, f of 2, is a minimum. Okay? And so let's actually take a look at that. I have a picture. Let me look at. Okay, so this is a very interesting graph, okay? That looks like this. Okay, so this is the graph of that. And you do notice, right? Let me zoom in here a little bit. That there's my two minimum points. See, I get come to sharp points. That's because my graph is continuous there, but the derivative doesn't exist. That's why I get these sharp points here. And they're both low points on my graph. And then I get this high point here at 0. I mean, it's not the highest point, but they're all relative extrema. So I get the two mins on the ends and the max, right? So very interesting looking graph. And then so you can also tell from the picture, but I have g of -2 is 0. So I get -2, 0. That's my min. And then I get 0 and 2.5 approximately. And that's my max. And then I also get 2, 0 on the other side as well. Okay? So that's my picture. I just wanted to show you, the algebra matches up. All right. All right, moving on. Another one. All right, so this time I have to remember that my f of x actually does in fact have a domain restriction on it. So that may make a difference when we're trying to find our min and our max somewhere along the way. Now this one, again, I need to find the derivative. I'm trying to find my relative extrema. And the first thing I need to do then is to find f prime. So f prime of x, I'm going to have to work a little bit harder this time. With each increasing derivative, it gets a little bit more challenging. And I want to use the quotient rule first. I don't want to, but I have to, right? So my derivative will be the bottom times the derivative of the top. The derivative of the top is 2x minus 2, and then minus. Now I have the opposite, this time x squared minus 2x plus 1, times the derivative of the denominator, which is 1, so I'm not going to write it, over x plus 1 quantity squared. Now, I'm going to get my 0 from the numerator, and I'm going to get my undefined places from the denominator. Now, I know that my undefined place here at x equals -1, right? I can do that right away. X plus 1 equals 0, x equals -1 is a critical number. But because x equals -1 was not part of my original domain, regardless of whether my graph changes sign at -1, it still can't be a min or a max. But it can be a place where my graph changes sign, so it's still important for me, and I still need to put it on the number line. Because if you remember, at vertical asymptotes, my graph can completely change behavior on the other side. All right, so let's clean up the numerator then. All right, so I'm going to multiply the top together, this first two. That would give me 2x squared plus 2x minus 2x minus 2, right? So there's the 2x squared. I get a positive 2x from here. I get a negative 2x from there. And I get a minus 2 on the end. And then I'm going to distribute through this minus sign as well. So minus x squared plus 2x minus 1 over x plus 1 quantity squared. All right, so what is my f prime of x after I clean it up here? These two cancel each other out, which is nice. I get a 2x squared and a minus x squared, which gives me a positive x squared. So I've used these two. I have a plus 2x, and then I have a minus 3. So now that I have my first derivative all cleaned up, I am ready to use my intervals of increasing and decreasing. So the first thing I need to do is find my critical numbers of the first derivative. And so I'm going to set the numerator equal to 0. This gives me x plus 3 times x minus 1 is equal to 0. giving me critical numbers of x equals -3 and x equals +1. Then I also get a critical number from the denominator, which is x equals -1. Now, this is not originally part of my original domain either. I still need to put it on my number line, but I know that it will not be a max or a min even if I change at that interval. So -3, so I have -1 here, and I have +1 over here. So I want to check in each one of these intervals, reminding myself that this here is a vertical asymptote. All right, so I'm going to pop in some values here. So I'm just going to look at the sign of these numbers again. So I'm going to look at f prime of -5, and when I do that, let's see, I will get a negative number here and a negative number here, so I'll get a negative times negative is positive on top. Then on the bottom, I will get something squared, which will be positive. So it's positive in that interval. I also have, let me try f prime of -2. Right, if I plug in -2, so I'm using this factored version. Let me write this like this, all over x plus 1 quantity squared. All right, so when I plug in -2, I will get a positive number here, a negative number here, immediately it's negative overall, and positive on the bottom. So this is negative in this interval. So that makes my -3 here a maximum point. All right, let's see, if I check between -1 and 1, that's f prime of 0. That will give me a negative number over a positive number, meaning I have a negative in that interval. So I don't change signs there. And then f of +2, for instance, would be positive times positive over positive. So it's positive here. So I'm going to have a, based on this, right, it didn't change signs here anyway, but even if it had, it wouldn't be a max or a min. So at -3, f of -3, I'm going to have a max point, and at 1, f of 1, I'm going to have a min point. And then the last thing I just need to do is pop these values back into my original. So let's come back up here to our original. F of -3 will be, I get 9 plus 6 plus 1 over -2. So this gives me, what, 16 over -2, which is -8. So there's my max point is -3, -8. And then I'm going to pop in my 1. And when I do f of 1, I get 1 minus 2 plus 1 over 2. And so this ends up giving me 0. And so that is my min point.